Hi, thank you for attending my talk on JCheck.jl, which is my attempt at property-based testing on Julia. If you want to access my slides online, you can do so by scanning the QR code in the upper right corner. So here we go. Testing is the act of validating a software, and a closely related concept is unit testing, where only a part of the software is tested. The part is called a unit. Usually the way it works is that you know the correct output of a unit given an input. You provide the input to the unit and make sure that the output matches what you expect. This can be done pretty easily in Julia using the test module. For instance, if you want to test this function here that returns true if and only if x is 42, you can use the test macro. And here you see that if we provide 41 to the function, it should return false, and this is what happens, so the test passes. Another way of testing software is called property-based testing, where we specify properties instead of outputs. It often relies on random input generation, although this is not mandatory, and for that reason it's closely related to fuzzing. For the rest of the talk, we're going to use the free group on a set as an example. Given a set S containing symbols like A, B, C, etc., you can generate the inverse set, which contains the same symbols with a little inverse mark here. And any product of symbols of the union of those sets is called a word. So for instance, if S is the set ABC, inverse S is inverse A, inverse B, inverse C. A simple word might be W naught here with those letters. And as you can see, we have C and inverse C adjacent in W naught. We can delete them. This operation is known as a reduction. And by doing so, we get the reduced form of W naught. So Fs is the group formed by the set of reduced word on S, together with concatenation. This means that concatenation is associative, which should be obvious. If it's not, you can prove it by induction. There is an identity element, which is the empty word, and each element has an inverse. So the inverse of a word omega is the word such that when you concatenate it with omega, you get the empty word. Right, so let's look at the implementation. I'm going to go fairly quickly over implementation details. The complete code is available on my GitHub. A way of implementing the free group is to have a type for symbol, a type for word, and given a certain function to operate reduction on vectors of symbols, you can force words to be reduced. It's very important, otherwise you don't have a group. And you need some functions to do stuff like concatenation, you need the identity element, and you need, well, you don't need, but it's convenient to have macro to construct words. So in order to perform property testing, you have to generate inputs for your units. In JCheck, this is done by overloading the generate method. So this is a possible generator for the type word. So it takes 3 arguments: a random number generator, the type that we're generating from, and the number of input we want to generate. So the generate function doesn't have to be random, although most of the time it will be. And well, the details are not very important here. In order to perform the test, we first have to create a container. This is done with the quick check constructor in JCheck. So you see here that QC has no predicate and no free variable yet. So let's say that we care about the inverse property. First, we have to implement the inverse of a word. This is pretty easy to do because the inverse of a word is computed by inverting each of its symbol and then reversing the word itself. This is implemented here, and the predicate is implemented here. In order to add it to the container, we use the add predicate macro, which takes the name of the container as first argument, a short description, and the predicate in the form of an anonymous function. We see that QC now has one predicate and one free variable. So the inputs are generated as soon as a new variable name is used, and the inputs are reused later if the same name is used. So it's efficient in that sense. To run the test, we use the quick check macro, and we call it on the container for which we want to run the test. Here we see that the unit test in QC passes. It's maybe a little bit more interesting to integrate the test in a test set. This can be done seamlessly with JCheck. You can use it along your regular Julia tests. It gets a little bit more interesting when we get a failing predicate. We know that FS is not commutative, so if we add the commutative predicate to QC, we should get a bunch of following cases. So this is the implementation of the predicate. We add it in the same way to QC. QC now contains two predicates and two free variables. So notice that the word is reused. And when we run it, we get this output. So we know that the predicate doesn't hold for some valuation. There is one valuation here, and JCheck by default serializes the failing cases to a file on the disk, so you can read it and experiment with it later in order to get a better debugging experience. Alright, so I'm going to go over a few other features of JCheck. One nice feature is the support for special cases, which are non-random inputs for your units. You can do it without JCheck, but sometimes it's a bit more convenient to do it through JCheck. And it's fairly easy to do. You only need to implement the special cases method. Another nice feature is a shrinkage. So you can tell JCheck how to simplify failing cases for you. This often, makes it easier to find the root of a problem. In order to do so, you need to implement the shrink and the shrinkable method for your type. And once you do it, for instance, we did it here for the type word, you get much shorter failing cases, which are hopefully easier to analyze. JCheck ships with shrinkers and generators for a lot of base objects, so a lot of the time you don't have to implement them yourself. Anyway, thank you for your attention and happy testing.